Good morning. So today we are going to discuss about a specialized operation which is called hashing. So hashing is both the store operation as well as a searching operation, which means you can use hashing for store a data into a particular data structure called a hash table, as well as you apply the same hashing technique to know whether a particular element exists in a hash table or not. So hashing is uh, just to be very simple. It is an implementation of hash table. So hash table is nothing but a specialized data structure. It looks like an array. It will have continuous memory locations, but one problem is that you cannot insert it in the same way as you insert it in an array. You will have to follow some rules, and those rules by which elements are stored into the hash table or are being searched for inside the hash table is called a hash function. Okay, so always there will be a hash function. The hash function will be applied over the elements that are to be stored, and then you identify the position where you can store the elements, and this process is called hashing. So hashing, the very good advantage of hashing is that it will have a time complexity always of a constant time, which means big O of 1. So whether you are applying it for storing an element, whether you are applying it for searching for a particular element, you can be assured that you will complete your task in a constant time, and that is the advantage of hashing. Whether you are going for a worst case, whether you are going for a best case, or even an average case performance, always your time complexity will be constant time, and that will be big O of 1. So that is the advantage of hashing. Now, talking about so keeping this as the advantage, there is one disadvantage for hashing, that you cannot store the relative ordering or relationship that exists between the elements of a data structure. So if you are talking about parent node, child node, or if you're talking about the elements having a value greater than or elements having a value lesser than, all those relative ordering will not be applied or will not be even taken into consideration in the case of a hash method. So that is the disadvantage. You cannot effectively represent the ordering or relative ordering that exists between the data elements, like that you have in a binary search tree or even a binary tree or even a heap. So that is the disadvantage of hashing. But one good advantage or the promising advantage of hashing is that it has got a time complexity of big O of 1, giving a guarantee that even if you are giving or even if you are going to search inside a very huge database, you can be assured that your result, whether it is there or not, will be available in a constant time. So that is the advantage of hashing, and because of this advantage, hashing is the technique that is being used in very large database systems like airline reservation or banking or even telephone database. All of them are making use of, very huge databases are always making use of hashing as their searching strategy as well as storing strategy. So let's see into the details of hashing. So always remember, we have three keywords while you're talking about hashing. The process hash. Hash stands for the process of mapping a particular element to be stored into a particular index of the hash table. So the second keyword is hash table, which is an array like data structure and is capable to store elements consecutively. And third one is hash function, which are those rules that you're going to apply over the elements to be stored so that you can identify the position where you can store the element in the hash table. So these three keywords are going to rule the process of hashing throughout our discussion. So let's start with the details of hashing. So when you talk about the general idea, you have got an array of some fixed sizes and it is going to contain the item. So hash table is an array like structure. Okay, it will have a index starting from 0 to n minus 1. It will store elements in a consecutive fashion. Then whenever you store that element is termed as a key. Okay, and this key will be used to compute the index of the position where you can store the key. Okay, so the data to be stored is called a key. You are applying the key into the hash function, and the hash function will produce or will be giving as output an index value, and that index value will decide the position of this particular key or this particular data item in the hash table. Then a key can be anything. You can have an integer, you can have a string, whatever it is, it can be anything. So what is the type of key? According to that, you will have to rewrite your hash function. Okay, it will not be always the same for all the hash tables. It will be entirely different. So based on the keys to be stored, you will have to identify what is the proper hash function by which you can successfully store all these elements or successfully make your search inside the hash table. Then the size of the array, since here you are not going to talk about array, it is your hash table. So the size of the array or the size of the hash table is mentioned as table size. Then as I said before, we'll have indices. So these indices will have a value ranging from 0 to the size of the table minus 1, which is table size minus 1. Okay, and the process of mapping the key to the indices is called a hash function. So this is a pictorial representation. So here you have got these many items. Okay, these many items. So here one key is John 25,000. The next key is Phil 31,250. The third key is Dev 27,500. Mary 28,200. So this pair of a name along with their salary is one single key. Now you're going to give the key into a particular hash function. It can be anything. So that is the decision taken by the designer. So that hash function is applied, and according to that hash function, you are going to map them into so many indices from 0 to 9, because this hash table is having a size of 10. So indices will be from 0 to 9, and you understand that John is in index position 3, Phil is in index position 4, Dev is in 6, and Mary is in 7. So this is the result of the hash function. So for John, while it is being applied, the hash function is producing the index as 3. For Phil, it will be 4, and so on. So this is the pictorial representation or the idea of how hashing is done. So this is a very important topic, or one thing which you would be using in your entire career, because you will be obviously you will be going to deal with databases, you will be dealing with the reservations and so on things. So wherever you can apply, hashing has got a prominent role. So please do understand this. Please do take this with utmost importance, and please do practice all these hash functions and the collision resolution and so on. So moving further, we'll talk about various hash functions. So a hash function, as I said, it is a set of rule or a function that governs the mapping of key to index. So your input will be a key and your output will be an index where the key cannot be stored. Okay. So the properties of a hash function, you will have a lot of properties to satisfy. But when you talk about a hash function, an optimal hash function, it should be always simple. It should not be too complex to execute, because as you increase the complexity of your hash function, your time taken will also be increased. Okay, so and that affects the performance of the system. So make sure that it is as simple as possible. It should be easy to compute. Okay, that means it should give the result in a minimum time. Then it should distribute the keys evenly among the cells. Okay, so that is the second important property, which means if you are given with a table size 10 and you are given with a 10 elements, the hash function, a good hash function, could be able to map all the elements evenly into the hash table, which means one in each location. Okay, so if the hash function could evenly distribute, then you can say that it is a perfect hash function. Then, if we know which keys will occur in advance, we can write perfect hash functions. But That is not in the real case. Okay, if we know in advance that these are the data that are to be stored, okay, then you can design a perfect hash function and you can say that this is my ideal hash function and it will be very simple to execute. It will give results in so many time, and it is going to evenly distribute the content. But that is not the real case scenario. You are not known about what is the type of key that would come. So always you have to take a generalized approach to build a hash function, because the hash function is built in the program coding level, whereas the inputs are going to come when the user is going to interact with the system. So always make sure that you create a hash function which is as good as possible. Okay, now some problems are there with the hash functions, like that we see in the previous example. The keys may not be numeric, so you cannot take a numeric hash function all the cases. Then number of possible keys may be larger than the space available in the table, which means you are having a table which is capable of handling 100 elements, but the user is flooding in 200 elements, so that is practically not possible to handle inside your hash table. So that is another problem that a particular hash function or a hash table may encounter. Okay, so if you can create, or if you can propose some mechanisms by which you can even handle elements more than the actual size of the table, then you can claim that your hash function is perfect. Okay, so whenever you can see that different keys are mapping to the same location, that is also a problem. Which means there was in the previous example we had John, we had Phil, then we had Dev and Mary. Suppose John and Dev are mapping to the same index position 3. That process or that phenomenon is called collision. So whenever you are going to design a hash function, you have to be clear that it is having zero or minimum collision. There should not be a collision at all. So if in case the hash function is producing collision, then you should also propose what is the possible way out to resolve the collision. Okay, so putting all these together, that is the problem of hashing, or that is the whole effort that is required in hashing. You have to first design an ideal hash function. It will not be ideal, you can say that it is optimal. Okay, so you have to create an optimal hash function. Then you have to make sure that the hash function can evenly distribute the elements. Then you have to resolve the collisions with minimum time that may occur in your process. Okay, so let's see about the hash function. So if the input keys are integers, then a perfect hash function can be a key modulus table size. Suppose earlier we had a key of earlier we had a key that was having both string as well as numerics. But suppose you only have numerical values, and your hash table is of size 10. Then uh, the key modulus 10 can be a perfect hash function. Okay, key modulus 10 or key modulus 1000. Okay, that can be also a perfect hash function. It will result in some indices. You can just go to that index and keep this data there. That is also possible. Then unless the key happens to have some undesirable properties. So if all the keys end with 0 and we use modulus 10, then what happens? All the keys are ending with zeros and you are taking modulus 10. What happens? Always it will result in 0 only, right? So which means all your key values are going to map into the same location, and that results in collision. Now, if you're having keys that are strings, then you will have to produce some other kind of hash functions which can handle string values. Okay. So, either you can go to convert it into a numeric value, or you can convert it into it as key values and then perform a hashing on it. So, I'll give you examples of all that. So, I'm just giving a generalized idea on what is hashing, what is hash function, and so on. Okay, so these are some methods. You have truncation. We'll see in detail all these hash functions. So some methods that can be applied for digits or numerical keys is truncation, where you can have a key, a larger key, you are going to truncate, or you are going to discards the last three values of the elements, or last three or four digits of the key, and then you perform a hash function on it, then you take the index. So that is also possible. Okay, so here in this case you have a key which is having 1 2 3 4 5 6 and 7 8 9 as the key value. That is one single value. So 1 2 3 4 5 6 7 8 9 is one single value. You are having a table of 1000, a table size of 1000, then which means the indices will be from 0 to 999. Now what you're going to do, you're going to pick any three digits. Okay, it can be either 1 2 3 or 4 5 6 or 7 8 9, or you're going to take it as 2 4 6, any three digits, but it should be the same applied to all the keys. Where if you're going for 1 2 3, then all the other keys should also take the first three digits. Okay, so the rule will be same for all the key. Now based on that, you are just producing the modulus, and then you take the corresponding index value. So that is also possible. Then second one is folding, which means you are going to take it into three subparts. You take the sum, then take the modulus, you get a value. That is folding. So there are various types of folding, and this is just an introduction. We'll see all of them in detail. Then the common one is key modulus n, where n is the table size. So if you actually want to happen the even distribution of elements, you can go for a table size which is a prime number. Okay, so which is a prime number. The advantage is that you can control the collisions, because only one and this number will be the factor, so you can ensure that no other numbers actually map into the same location. So if you can fix the table size as a prime number, that is very good. Then second one is squaring. The next one is squaring, where you actually take the square of the key, then truncate it according to your convenience, find an index, then map it to that particular index. Radix conversion, where you have it is initially the numerical value will be of base 10, decimal number base 10. You have already learned in your logic systems and all. So base 10 you have to convert it into another base. It can be a base 11 or whatever it is. You are just taking it into the another base. You get another value, then you truncate if necessary. So these are some methods that can be approachable for hashing, where the key values are numerical values. So this is in the case where the key values are strings. Okay, so there are 2 3 examples for strings. Here this is a hash function. So this is function, so it is going to accept a string. Okay, and it will be taken as a pointer value, and this is key, which corresponds to the first. It will be first having the first character address. Then you have the table size, so you have a hash value which is initially 0. Then what you do, you're going to travel through the key. So the key may be having n number of characters, so you have to travel through all the character, find out its ASCII value, add it to the hash value, then you apply the modulus, you get the desired index. So I'll just explain. So suppose you are having an string which is saying a name called Pooja. Okay, so then string is actually Pooja. So it has got 5 characters, Pooja. Now what you do, you are passing it to the hash function. So inside the hash function, initially the hash value will be equal to 0. You are taking it into the loop. You are starting from the index position 0, the starting position 0, where you have the character P. Then you have the next value, which is O. So once you have P, what you do, you take the ASCII value of the character P. Okay, you take the ASCII equivalent of the character P, you add it to the hash value. Okay, you add it to the hash value. Okay, so that value is added. So hash value now becomes 0 plus the hash value of P. Sorry, the ASCII value of P. Then this process will repeat. You take the ASCII value of O, then you take the ASCII value of O again, then you take the ASCII value of J. All these are added into the hash value. Now the hash value will be having some significant value. Then you apply it, and it will be obviously numerical value, because ASCII is the numerical equivalent of the character. So what you do, you will apply the modulus, which is of the table size. Table size, you would be taking it as a prime number. So table size, it is applied, you get an index, and you store the element into that particular position. This is how one method of finding the key value for a string key. Okay, finding the index value for a string key. So this is simple, and you can implement it very simple, but if the table size is too large, then you cannot ensure that the keys will distribute well. So that is one single problem with this one. Okay, so if the table size, that is here given as an example, if the table size is 10,000 and the key length is less than or equal to 8, the hash function can assume only values between 0 and 1016, because the key value is always less than or equal to 8. So the maximum that you can make is ranging between 0 to 1016. So what happens? All the keys will be distributed between the indices 0 to 1016. The remaining portion, this was having a table size of 10,000, the remaining entries will be left unused. So that is not a that you cannot take as a very good hash function. Taking another example, here what you do is you are taking the first three characters of the key. Okay, so you have a key which is string. So you take the first three characters. Then what you do is you take, again you are going to take the ASCII value, but you are applying some computation along with the ASCII value. So what you do here is you take key plus 0. You can take it as in this other example also. You can take it as int hash value is equal to 0. You can copy it there. Then for int I is equal to 0. That can also be done here. But this is taken as a kind of a straight example because you are taking only the first three characters, right? So what you do, you for the first ASCII value, suppose it was Pooja again, you take the ASCII value of P, then you add 27 to it. Okay, then you multiply it with the ASCII value of O plus 729, that corresponds to 27 square, into what is the third part? The third part is ASCII value of I'm really sorry. This is the first case. You are going to take the key value, which is ASCII value of P. You take the value as P, the ASCII value of P, then into 27 raised to 0. Okay, 27 raised to 0. So that is actually 1. So it is taken as the ASCII value of P itself. Then you take 27 into what you are taking, the ASCII value of O. So that will be taken as 27 into the ASCII value of O plus what is the third character? It is again O. So you take the ASCII value of O and you multiply it with 729, which is the ASCII value, which is the square of 27. Okay. So this is another example, and again you are applying. So you get some numerical value, you apply the modulus, you get the index. Okay. So this is taken, why 27 is taken is because English is said to have 26 characters. So you can produce a maximum of 17,576 different words using a 3 key value. So that is why you are just taking it as 27 to take that 1 to 26 characters of English. That is why you take it as 27. Okay, this function is although easily computable but not appreciable if the hash table is reasonably large. So these are some examples. There are a lot of examples which you can apply for values which are strings. Okay, you can just Google it, you can understand, you can take some examples, you can learn for yourself also. There are a lot of examples. I have just quoted 2 because these were very simple to understand. That is why I have just quoted 2 or 3. Then properties of good hash function. So properties of good hash function, we know it should always have a value which is ranging between 0 to the table size minus 1, which means it should always produce an index value within the range of indices. Then it should be efficiently computable, which means whatever be the key, you should be able to compute it in a constant time or a time complexity of big O of 1. Then it should not waste the space unnecessarily, which means it should be able to evenly distribute the data. There should not be clusters somewhere, then a group of elements being stored adjacently, then you have a lot of spaces being vacant, then you have another group of elements being stored adjacently. That is not a good quality for a good hash function. So you have to ensure that it should evenly distribute the data elements. Then the last but the most important thing is it should minimize collision. So you cannot say that it is a zero collision because that is in the case of an ideal hash function, but you have to ensure that it is minimizing the collision. So even if there is a collision, you can propose some collision resolution strategies also, but make sure that the collision occurs in a minimum level. Okay, so these are the properties of a good hash function. If you can claim all these properties in the hash function that you design, then you can say that it is a good hash function. So integer keys, I said it is hash of x is equal to x modulus table size, where the table size is generally chosen to be prime to avoid the collisions. Then, yeah, because the keys are typically not randomly distributed but usually have some pattern, so we can see that it will be mostly multiples of 10 and so on. It will be mostly having some order, so you have to break that order. In that case, you can take the table size as uh, prime number. Okay, then if k is the factor of table size, then only table size divided by k slots will ever be used. So whatever be the table size that you take, if k is taken as a factor of table size, then you can say that only table size divided by k slots will be ever used using that hash function. Since the only factor of a prime number is itself, this phenomena only hurts in the table in the case where k is equal to table size. Okay, so that is about making the table size prime. Now, strings ASCII can get an integer by adding up the ASCII value. This we have already discussed. Okay, so we are just taking it as the same thing. So one problem with this particular hash function is that if you are having same values, okay, so the first key was ABC, the second key was BCA, the third key was ACB. All these are having the same characters. So if even if you take the first three characters, they are exactly the same, which means whatever you do, the ASCII value summed together will get the same numerical value, which is applied to the modulus function. It produces the same index. That means it results in collision. So this was the problem associated while you are having strings as keys. So this is another example. Here you are not taking 27, you are taking 128. So the first character, the ASCII value will be multiplied with 128 square. The second character, the ASCII value will be multiplied with 128, and the third character, the ASCII value will be added as such. Then modulus table size. So what happens is, since you are taking a much bigger value, this will result in better performance. Okay, then making the string hash. So this is one example, the honors rule. So what he has done is that he has not just taken the hash, not just taken the ASCII key, he has also performed a left shift. Okay, so he has just performed some left shift also. So that also made it more better, which means it could reduce the collision. Okay, so even if you are getting the same value, you are performing a left shift over it, so that you get a different value, and then you apply it over the table size so that you can get you can reduce collisions. Okay, so all the other thing remains the same. Okay, you are just taking the key at you are taking the ASCII value, then you are performing a left shift by 5 digits or 5 bits, then you apply it over the table size, you get the value. So minimum number of multiplications, because everything is handled by shift, then it avoids overflow because you are using modes of modeless during the computation. Then talking about the optimal hash function, as I said, it should be simple, it should be uniform, which means all the keys should follow the same rule. Then maps each key to a fixed which is a random number. Then it should be, if it is ideal, then it will have zero collision, which means a gold standard. Then it is very simple to analyze. Then it should be closely approximated by the best hash functions. So these are the properties of optimal hash function. So I'll give you an example here. So this is not an optimal hash function. This is just to let you know how the hashing process is done. So here you have got some keys 10, 19, 35, 43, 62, 59, 31, 49, 77, 33, so on. Okay, so what is the hash function that is being applied here? This hash function is the sole responsibility of the program. Okay, so he can design any hash function which he can claim that it will minimize collision and it will be producing in a lesser computation time. Okay, so what is done here is you add the two digits in the key. So if it is 10, you add it together. So 1 plus 0, it gets 1. Then what is the digit at the units place? Okay, so in the units place, what is the digit? So when you add 1 plus 0 in the unit place, you have 1. So 10 can be stored in the in that particular index. Similarly, if you are going to take 1 plus 9, you have in the unit place the index value 0, which means you have to store 19 in the index position 0. So this is how it is done. You can see the pictorial representation here. So 0 is stored in, 0 is filled with 19, 10 is stored in 10, 10 is stored in 1. Then 4 plus 9, it was 13. So in the unit place, you have 3. So 49 is stored here. 59, 31 and 77 all corresponds to the same index. And this is something which we call collision. Okay, so this is an example of collision. So what you can see, all of them are mapping to the same index. You cannot store many values in the same index. Okay, so that scenario is a collision. Okay, so you have to perform collision resolution strategies that we learn later, and then you see that it is resolved. Okay, so this is an example of this hash function. So these are the indices. You understand which are the indices, then you store it accordingly. So this is how it is done. Okay, so this is actually the result of the hash function. So 1 0 resulted in 1, 1 9 resulted in 0, 3 5 resulted in 8, 4 3 resulted in 7, 6 2 resulted in 8 again. So this was a collision. 35 and 62 are mapping to the same index. 59 and 31 are mapping to the same index. Again, 77 is mapping to the same index. 49 is mapped to 3, 33 is mapped to 6. Then division method or the fast hashing method, which is the widely accepted or commonly used hashing method, which we have seen, modeless table size. Okay, so choose a number h which is larger than n and usually having a prime number. So if you have to store n elements, n keys, then you choose a prime number which is greater than n but closely related to n. Okay, so n is the number of keys in the available set. Then hash function is h of k is equal to k mod h. Okay, where k is the key, h is the table size. Then you will have indices starting from 0. If you are having indices starting from 1, then you will have to take k mod h plus 1. Okay, so this is one method, the division method. All of these are examples of hash functions. Okay, then you have the mid square method where you take the appropriate number of bits or digits from the middle of the square of the key value. This can be done in two ways. Either you can take the middle of the key, then take its square, then apply it over the index, or you can square the key, then you can take the middle value, then you can apply it over the index. Both of them are actually mid square methods. Okay, so it can be applied in two ways. Either you can take the square of the key, then take the middle value, or you can take the middle value, then apply the square to get the value. Okay, both are accepted. So that is mid square method, but the limitation is it is kind of time consuming because you have to perform the squaring, then take the truncation, applying all that. So it will take time. Advantage is that you can ensure that it is having uniform distribution. Talking about folding method, folding method is of three types. We have seen the pure folding method where you had 1 2 3 7 1 2 3 4 5 6 7 8 9 as the key. You divide it into three groups, each having three digits. Then you add them together, get a value, then you apply truncation if necessary to identify the index. So that is folding method. Fold shifting is that you get these values. So suppose it was 1 2 3 4 5 6 7 8 9. What you do is that you apply some shifting. Okay, suppose 1 2 3 is the first part, 4 5 6 is the second part. Instead of 4 5 6, I am going to write it as 6 5 4. So that is actually shifted. Then you write 7 8 9 as such. Then you take the value. That is fold shifting. Okay, so suppose if you are having a 16 digit key, okay, then you have four parts. Okay, suppose if you are taking as 4, then you have four parts. So you can apply fold shifting as you are shifting the first and third keys, or the first two keys, first two parts, then the others are kept intact, or the last two parts, the first ones are kept intact, or the second and fourth, any combination that you apply that you can do, but make sure that the same rule is applied across all the keys. Okay, so that is fold shifting, which means you are going to shift or reverse the subparts. That is fold shifting. Then you add them together, apply truncation if necessary, identify the index position. Fold boundary or boundary folding. There you are going to shift only those parts which apply in the boundary, which means the first part and the last part will be reversed. All the other parts will be kept intact. So that is fold boundary or boundary folding. What you can do is that you can take some examples. Okay, you can take some big keys. You can take a hash table of size 7. Okay, you can take a hash table of size 7. You apply pure folding, fold shifting and fold boundary. You get a sum. You apply that sum modulus, or if you want you can truncate according to your wish. The truncate means you can remove some values from the sum, but always remember, if you are removing the last value from the first sum, then you have to remove the last value or last digit in all the corresponding sums that you apply. Okay, do that. Then identify what is the key value that can be applied. Apply it. You identify the index. Then you can store this big key 1, 2, 3, 4, 5, 6, 7, 8, 9. That big key can be stored in that index position. You can take examples for that. There are lots of examples available in internet. You can just go through and do it for yourself. So I have taken an example here. This is for pure folding. So here you have these many elements. What I do is that I make them uniform. Okay, I make them uniform, then I apply it, you add it, you get some value 369. It was a table size of 1000. It was capacity was 1000, so 0 to 999. So what I do is I omit this one. It was carry, that is omitted, so I have 369. So 369 is my index, and this big value 345 567 7234 will be stored in the index 369. So this is how it is done. So if you want to truncate for 2 digits, you can do that. If you want to truncate for 3 digits, you can even do that. This is in the case you are truncating only the carry. But if you want to do it like you are truncating the first 3 digits, you can do that. Or if you are truncating the last 3 digits, you can do that, no problem. But it is better to truncate with the carry, because in most cases you have the carry as 1. So you can take it as 136 being taken out. If you have the table size of 10, then you can take 136 away. You can take the last value, which is 9. That is also possible. Okay, so whatever you do, it should be applied for all the keys in that list. So that is the only thing that you have to follow. Next is digit analysis method. So in digit analysis method, what you do is you are going to have a long key. You extract some digits from that, and based on that value, you take the index. So that is digit analysis method. Okay. So I'll give you an example here. You have 6732541. Okay. 6732541 is my key. What I do is I extract digits at even position. So what are the elements available in the even position? 7 is in the position 2, 2 is in the position 4, 4 is in the position 6. So I have 7, 2, 4. Now I have 7, 2, 4 being the extracted digits. What I do? I apply reverse. So it becomes 4, 2, 7. If necessary, you can apply truncation or modulus table size over that. Then you can get an index position. You can store the value there. If you have a table size of 0 to 1000, you can take 427 as the address itself, and you can store 6732541 in the index position 427. Okay, so this is an example of digit analysis method. So for each criterion, the hash addresses are calculated. Then you can actually plot a graph. The criterion which produces the most uniform distribution is chosen. And uniform means it should be having a graph with smallest peaks and valleys. So that is about digit analysis. You don't actually have to plot the graph in our example. You can just make use of your hash function. Then you can deliver the best hash table. Okay, so these are some examples: 2234, 3452, 2784. So here what we did is that In the second position and the third position, digits were extracted. So the first key 2 3 was extracted, in the second key 4 5 was extracted, and the third key 7 8 was extracted. Okay. Then what happens is, address with no rearrangement is 2345. It's not 62, it's actually 78. I think it was a mistake. Either I missed a value or it was a mistake. Okay, so it is 23 45 and 78. So if you want, you can rearrange it as 32 54 and 87. Okay. Then the next one is direct addressing. Direct addressing is not very common because direct addressing says that whatever be the key value, that will be the index. So if the key value is 10, 10 is the index. If it is 96, it will be the index. What if the key value is too large? Then you will have to make sure that your hash table is also too large. Because of that, we are not using it so common. Okay. So this is direct addressing. If you have a small table, then this is the best choice that can be applied, but that will not be in the common case, so we are not generally using it. So this is direct addressing. So throughout all these slides, I was explaining various types of hash functions. We have seen modulo division, we have, which is the very common one among that. So if you can choose a table size which is a prime number, then you can minimize the collision also. Then we have discussed about mid-square method, digit extraction method, truncation method, then direct addressing method. All of them are examples of hash functions that you can apply over a key which is numerical in nature. We have also seen honors rule and some other examples which use the ASCII value for string keys also. So all these are examples of hash function. So one problem that could encounter while you are performing hashing is collision. So in the next video, we'll be seeing how to reduce collisions or what are the collision resolution strategies that you can apply for making your hash table the best. Okay, so that will be discussed in the next video. So thank you. If you have any doubts, you can ask me. Else, I recommend you to go for your own examples, or you can even refer to the internet, take some examples, take some hash functions, apply it over, do it for yourself so that you can understand it better, because this is one of the sure questions that that can be expected in your final examinations. Thank you.